Oh, what's up? AP Stats guy here, right here up in my room with the whiteboard, and I'm going to be doing chi-squared goodness of fit. This is the second video of chi-squared. So we're actually going to do a hypothesis test. And just like all hypothesis tests, I use 3 steps. The last step's kind of complicated, but there's 3 steps because I don't want you to forget the first 2. Here are the 3 steps to hypothesis testing that I always use. 1, the 3 steps. Make a null and alternative. That's the step I called ho-ha. Don't forget your null and alternative because you have to assume the dull hypothesis. You need something to think, well, if you say, if this is true, and then here's what we expect, that's how you set your expectations. So you have null, alternative, then draw a null model. Your null model is your pile of statistics you'd expect to get if you took a bunch of samples if the null was true. So you're saying, if the null was true, and I took a bunch of samples, this is what my pile of statistics would look like. What's the pile of statistics? Well, it could be a pile of x bars, a pile of sample means, or a pile of p hats if you're taking sample proportions, or a pile of x bar minus x bars if you're doing differences, p hats minus p hats. But for chi-squareds, we're imagining a pile of chi-squareds. So we're going to sketch a null model for chi-squared, and we're going to think, what would be a strange chi-squared if the null were true? So from this model, basically, where's my chi-squared in this pile of chi-squareds? So we think, what would surprise us? Then we calculate and conclude. We basically find the test statistic, which in this case is going to be a chi-squared, and we're going to see what the p-value is. Is it beyond the rejection threshold? Okay, so what is a goodness of fit test? A goodness of fit is you want to know how good your data fits your hypothesized distribution. Does it fit or does it not fit? The null is always that it fits. The alternative is it doesn't fit, okay? Remember the dull hypothesis is like the boring hypothesis, the nothing interesting here hypothesis. So that's what we're going to be doing again. So here's the problem we have at hand. I'm going to slide this thing up a little bit. So what are we talking about? Is there an equal distribution of colors? Where in here? I've got these here. I'm saying, I wonder if there's an equal distribution. Now, it looks to me like there's more blues, but are there more oranges? I don't know. So I want to know, I don't want to count them all. I'm not going to look at every one and make piles of all 4 colors. I'm just going to take a handful. So that's what I'll do right now. Take a handful. I count them. Oh, I counted them, and I'm going to write them. Oh, here they are. Cool. So what I found out, I had 12 red, 16 blue, 4 orange, and 8 green in my sample. All right. I'm going to test a hypothesis. So what is my null and my alternative going to be? Well, I want to see if there's an equal distribution, okay? Because I feel like they're not. So I'm going to assume that there is an equal distribution and then look for evidence to see if there's not, okay? So my null is going to be colors are equally distributed, represented or whatever. My alternative is they're not equally represented. Okay, basically, it fits an equal distribution, it fits or it doesn't fit, okay? So that's my null and my alternative. Now, the question I'm wondering is, there's my ho and my ha, okay? Now, my null, they're equally, now if they were equally represented, so if there was an equal amount of each of the colors, red, blue, orange, and green, the exact same amount, and I took a sample, and you took a sample, and that guy took a sample, and oh, did you get a sample? If all these people took samples, and we all calculated a chi-squared, and made a pile of chi-squareds, what would that pile of chi-squareds look like? That's the sampling distribution. That's the null model. So I'm going to draw that over here. Now, we have 1, 2, 3, 4 categories. 4 minus 1, so we have 3 degrees of freedom. So a chi-squared with 3 degrees of freedom, I'll call it degrees of freedom, would look something like this. Remember we did this in the last video. The mean of the pile would be at the degrees of freedom, in this case is 3. The mode of the pile of chi-squareds is going to be at the degrees of freedom minus 2. Whoops, that's kind of bad. 3 minus 2, which is 1. And then the cutoff, the chi-squared, like the 5%, the alpha 0.05 cutoff region, is always 1.5 times the degrees of freedom plus 3. So that's my cutoff, or my rejection region. So we're going to do 1.5 times 3 plus 3, which is 1, 3, 4, 7.5. So I have these numbers, 3, 1, 7.5. So I can actually draw a chi-squared. So if these were equally distributed, and we took a whole bunch of samples, we'd get a pile of chi-squareds that look like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These three numbers are important. So I know that the balancing is at 1, 2, 3. So here's where it would balance. That's the mean. Here's the mode at 1, 3. And here's my rejection region would be at 7.5, 5, 6, 7. Here we go right here at 7.5. There's my rejection region. So what I can do is I can actually sketch a little chi-squared. This is the highest point. This is the balancing point, so it's going to look like this. Ooh, and only 5% is beyond 7.5. This is about where my alpha equals 0.05 is going to be right around there. So this is a pile of chi-squareds if the null was true. Okay, cool. So basically, I'm walking in this thing. All right, cool. I have 4 categories. 3 degrees of freedom. If the null was true and I took a bunch of samples and took a bunch of chi-squareds, I'd end up with I'm expecting a chi-squared somewhere around 3, 4, or 5. That's probably where I should. But if I get a chi-squared value way down here, that was unlikely to happen randomly. I'm going to reject the null. I don't think that the distributions, I don't think they're equally distributed. Okay. Now, what you're wondering is, how the heck do you get the chi-squared? Well, the chi-squared is always found the same way. All right, the chi-squared, you're following this formula. It looks fancy, but it really fancy and weird. You take basically, it's the sum of your observed value minus your expected value squared over what you're expecting. Now, you must be wondering, what are observed and expected? Well, what did I observe in my sample? In my sample, this is what I observed. 12, 16, 4, and 8. So this is what I observed. I observed these. What was I expecting? Well, it depends. What's your null? Well, my null is colors are equally represented. So I was expecting the same amount in every category. 4 categories, I was expecting 25% in each one. Well, how many did I take in all? What was the sample size? 40. 25% of 40 is 10. So I was expecting about 10 of each color. So here's my expected. So all you have to do now, I've got my observed, I got my expected. So now what do? I just do observed minus expected square divided by expected for each one. I'm going to do 12 minus 10 squared divided by 10, 16 minus 10 squared divided by 10, 4 minus 10 squared divided by 10, 8 minus 10 squared divided by 10. So we can do those out right now, and I'll show you what that looks like. Here we go. So 12 minus 10 squared over 10, 16 minus 10 squared over 10, 4 minus 10 squared over 10. Now, these aren't always equal. It could have had like a 30%, 20%, 30%, something percent, right? Instead, and then I'd find that expected. So the expecteds are a little bit, there's trickier. There's trickier problems than this for sure. 8 minus 10 squared minus 10. Now, this calculation are chi-squared contributions. So each of these categories contributed to the chi-squared. Some contribute more than others. The ones that contribute more are further away from what you're expecting. Those are like the big contributors. Those are the ones who may be like the ones you want to investigate in a post. It's called post hoc. So after you do the test, you go back and you're like a hawk after. You're like the post hoc. You're like, what's going on in there? Okay. So 12 minus 10 is 2, squared is 4. So we get 4/10 plus 16 minus 10, 6 squared, 36/10. 4 minus 10, negative 6 squared is 36/10. And 8 minus 10 plus 4/10. Oh, look at that. They're all tenths. What do you know? I can do it in my head. So this is 0.4 plus 3.6 plus 3.6 plus 0.4 gives me 4 gives me 8. So my chi-squared value is 8. That's my test statistic. Now, notice who contributed the most. The blue and the orange contributed the most. The blue is far away above what I was expecting, and the orange is much less than I was expecting. Those are the two biggest contributors, right? So now, how do I figure out whether or not I should reject? Well, let's look at our model. We were saying, all right, we were expecting a chi-squared somewhere around 3, 4, or 5, and we ended up with a chi-squared value of 8. Okay, does that chi-squared value of 8, where is that? That's beyond my 7.5. That's over here. My chi-squared in this pile is way down here. That's weird. So I know I'm probably going to reject the null because it's beyond the chi-squared cutoff. Now that was just using the 1.5 times degrees of freedom plus 3 rule of thumb for an alpha of 0.05. Sometimes they say alpha of 0.02 or alpha of 0.01. And alpha of 0.01 is just a few beyond that. But you can actually use your calculator to use, just like before we did TCDF, norm CDF. Well, there's a chi-squared cumulative density function that will give you the now it's super nerd. I know, you're like, cumulative density, what the heck are you talking about, Nystrom? What I'm talking about is there's a chi-squared CDF where you can put in your chi-squared value out to 99999 with the degrees of freedom in it, and it will give you the area under the curve. Now, we know that 7.5 is about the cutoff for an alpha of 0.05. We're expecting the 8 degrees of freedom to be less than 0.05, but let's do it on our calculator. Let's see, we'll go to on. I'm going to come over. I'm just going to go over here so you can see it clear. I'm going to go to second, clear, second distributions. I'm going to go down to chi-squared CDF, which is the cumulative density function. What's the area from a chi-squared of 8 out to a chi-squared of 99999 with 3 degrees of freedom? 0.046, so a little bit below 0.05, which is what we were expecting, okay? So we get the p-value below 0.05. So what I'd say in conclusion is with a p-value this low, I reject the null. There is enough evidence, okay? You reject when you have evidence. There is enough evidence, I'm rejecting this, to say that the colors are not equally represented in the bucket. Namely, it seems like blue and orange are off. It seems like blues are overrepresented and oranges are underrepresented. That's in my post hoc study. But what you're going to say is just with a p-value this low, I reject the null. There's strong evidence that, now if it was like an alpha of 0.01, we wouldn't be able to reject. But that's a chi-squared goodness of fit test in a nutshell, okay? So that's when you have one sample and you're asking one question, all right? These expected values, the expected values could be a little bit different. There's a couple other ways you can see the expected values. I'm just going to show you really quickly. You might say, instead, is there a 1 to 3 to 3 to 2? Is there a 1 to 3 to 3 to 2 ratio of the distribution? So in this case, you'd have to figure out if they're distributed how? Well, 1 to 3 to 3 to 2. You got to add these up. 3, 3, 6, 7, 8, 9. So 1/9 to 3/9 to 3/9 to 2/9 distribution. And you just multiply each of these by 40. So your expectations would be 1/9 of 40 in this one, 3/9 of 40 here, 3/9 of 40 here, and 2/9 of 40 here. So sometimes they're set up like they give you like a ratio. Sometimes they'll say, oh, they'll give you the percents. The bead company says, oh, 12% are red, 14% are blue, and then you'll just take that 12%, and multiply it by your sample size, 0.12 times 40, and you do 0.14 times 40, and you'll get that, okay? So your expected depends. It's just whatever the percent is, or the fraction, times your sample size, and that's how you find your expecteds, okay? Just be careful, though. Well, one of the ones that students usually get, the percent ones, they generally do okay. You just take the percent of that category times n. It's the ratio ones. Those come up in biology and stuff, and you're like, what the heck? How am I supposed to do this 3 to 5 to 2 to 2 ratio? I mean, are those percents? No, those aren't 30, 50, 20, 20. You actually have to say, well, if that's the ratio, you got to say, well, what do we have all together? 8, 9, 10, 11, 12. So this is 3/12, 5/12, 2/12, and 2/12 in each one of these categories. So you got to multiply that fraction times the sample size, and that's what you're expecting in each one. Now, some calculators actually have a goodness of fit test in them. And in the goodness of fit, if your calculator has it, you could have put L1, our observed, minus L, and L2, put the expected. And if you run the GOF test in your calculator, go to it and hit draw, guess what? It'll draw this exact model, and it'll shade from here and beyond. It's pretty cool. You want to see? I might as well just do it. Hold on a second. I'll get one. So if you're going to do this, remember we had observed 12, 16, 4, 8, our expected. Well, you can just take them and put them in your TI. You can take your observed and put them in L1, your expected in L2. And now that they're in L1 and L2, you can go to stat, over to tests, and you can go to the chi-squared goodness of fit test. and your observed is L1, your expected is L2, how many degrees of freedom? 3. We can hit calculate, and guess what? Get the same chi-squared value, 8, that we got by hand, the same p-value that we got, right? But and these are the contributions, 0.4, 3.6, 3.6, 4, so we can find what the contributions were. But if you go through it again and hit draw, guess what? You're going to get this little sketch that we have right here. Your calculator will sketch the exact same thing. So watch. If I go to stat, over to tests, and I go to chi-squared, goodness of fit test, and instead I go down to draw, guess what it's going to draw? Whoa, look at that. It looks a lot like this right there. Oh my goodness, same thing. Guess what? Where's the peak? Where's everything? It's everything you thought, right? P.046. So you get the exact same sketch. Okay, so I'm not just making this stuff up. All right, well, hopefully that helped you with the chi-squared goodness of fit test. Super cool test. I don't know. I like doing it, and hopefully you do too. Have a good day.